Hello and welcome to the third installment of Method of Images. In the previous two videos, we have already talked about divergence and curl in great detail. We have found out the mathematical expression of both of them, and we have also defined the Maxwell equations in differential form as well as in integral form. Right now, in order to understand method of images, uniqueness theorem plays a very big part. It is actually the base on which we are going to build on and get the method of images. So it's really important for us to understand this topic. And in the course of this video, what I'm going to do, I'm going to take several cases, actually four cases, and starting from the very basic one to the most comprehensive one. And I will prove a certain statement to you, which we are going to use in the next video, which is method of images for a spherical conductor, right? So without wasting much time, let's start the derivation and let's start understanding the uniqueness theorem. Okay, so the need of method of images, what method of images actually tells us, let's do a quick recap, is if we have a charge particle, if we have a charge and there is a metallic sphere, conductor, plate, anything, if a conductor is placed, then because of this charge, this point charge, some charge is going to get induced. Now this charge may or may not be uniform depending on whether where we have kept this q charge, right? Now if it is non-uniform, there's no way that we are going to find out what the charge density is going to be, but still we have to find out electric field and potential at some point p. To find that out, it is entirely possible we use method of images. To describe method of images, we need uniqueness theorem. So let's get started with the uniqueness theorem. What we have studied so far is the differential form of Maxwell equation, that is del dot E will give us rho by epsilon naught, where rho is the charge density, right? We also know that electric field is minus grad V, minus gradient of V. From the electrostatics, we already know this. Now, if we keep the value of electric field in the first equation, we get del dot del V equal to minus rho by epsilon naught. That is del square V equal to minus rho by epsilon naught. This equation is known as Poisson equation. Yeah, I know it's written as Poisson's, but it's called as Poisson equation. N is kind of silent, right? Where rho is charge density. Del square V is equal to minus rho by epsilon naught, right? If we have a charge free space, if we have, or in a charge free space, in a charge free space, we can write del square V equal to 0. This is Laplace equation. This is known as Laplace equation if rho is 0. Now, in first view, it might seem that del square V is equal to 0, Laplace equation. This is not going to give us a lot of results. But the fact is, it's a very important equation and it is going to be used in many cases, in many ways in electrodynamics, even in college, right? So del square V is minus rho by epsilon naught, that's Poisson equation, and del square V is 0 if we are going to apply this equation in a charge-free space. This is Laplace equation. Now what we are going to do, we are going to take four cases. In the first three cases, we are going to assume that the space is charge free, and in the last one, we are going to take the charge distribution also, and we are going to find out some results from those four cases. So let's get started with case one. Case one, case one is let's say we have a closed surface. We have a closed surface, and we already know a closed surface encloses a volume, correct? A closed surface encloses a volume. This surface, closed surface, does not have any charge density of any kind inside it, right? Now, our claim is what we need to prove in the first case is that there cannot be a maxima or minima of potential inside this closed surface or inside this volume, within this volume. We cannot have, we can't have a maxima or minima of voltage inside this surface, inside the volume. So the maxima or minima is going to be on the surface itself. It is not going to be within the volume, right? We have to prove it. Also, since the cavity is charge free, we can write del square B is 0. Definitely we can write this equation, right? Now, there are two ways to prove this statement that we cannot have a maxima or minima inside the volume. The first is very straightforward. Let's see. See, we already know from Gauss law that if charge is 0, if charge density is not there, there cannot be any electric field line which is getting originated from within the volume, or there cannot be any electric field line which is getting terminated within this volume. इस क्लोज सरफेस के अंदर से ना तो कोई इलेक्ट्रिक फील्ड लाइन बाहर जा सकती है नेट, ना ही कोई नेट इलेक्ट्रिक फील्ड लाइन अंदर आ सकती है. मतलब ना तो ये सोर्स हो सकता है इलेक्ट्रिक फील्ड लाइन का, ना ही ये सिंक हो सकता है इलेक्ट्रिक फील्ड लाइन का. So any electric field line that is going to appear within this volume will have to pass through it. It will have to come from outside and leave this volume, right? कोई भी इलेक्ट्रिक फील्ड लाइन होगी उसे बाहर से ही अंदर आना पड़ेगा और अंदर से वापस से वो बाहर जाएगी ही जाएगी. And we know that in the direction of electric field, potential decreases. We already know the fact that in the direction of electric field, potential decreases. So at any point within this volume, we can always say that the potential is decreasing along the line, along the electric field line, correct? So potential cannot have a maxima or minima within the volume, correct? Since potential is going to be decreasing at every single point on this electric field line, we can safely say that there cannot be a maxima or minima within this volume. It will always be either on the outside of this volume or on the surface of the volume. It cannot be inside. This is method 1. This is method 1. Now second method is method by contradiction. This is also going to be explanatory. A lot of things in this video are going to be explanatory. They don't have much of mathematics, or they will have very simple basic mathematics. So we don't have to be afraid of mathematics here, but the logic is going to be there, right? So the second method is contradiction. Contradiction, how to prove it by contradiction? Let's assume, let's say that we have a point A, a P, we have a point P which have, let's say, maxima. This point P, Vp is a local maxima of potential. We have assumed this. If at P there is a maxima, then definitely in any direction from P, in any direction from P, the potential should decrease. In any direction from P, the potential should decrease because it is a maxima, correct? Now, if the potential is going to decrease in any direction, in the direction of decrement of potential, electric field should be there. Electric field is in the direction of decrement of potential, correct? So what I have drawn these brown lines are electric field lines, because from that point P in every single direction the potential is decreasing. That means electric field is going outwards from P, correct? Now, if electric field lines are like this, then that means P should be a P should have a charge, a positive charge actually, because it is becoming a source. Electric field is getting originated, a point source, right? And we have already given that rho is 0 inside the cavity, everywhere inside the cavity. So our assumption that P can be a maxima is wrong. What we did is, if P is a maxima, then in every direction from P, there should be a reduction in potential. That means electric field must be in the direction of reduction of potential. And if electric field lines are getting originated from P, rho should be positive, and we have already given that rho is 0. This is the condition for case 1, rho is 0. Definitely, so our assumption is wrong. So by contradiction, we have proved that P cannot be a maximum. Similarly, if it is a minima, then the electric field lines will be converging on P. So rho will be negative, which is again a contradiction to our assumption, right? So we can safely say that in a charge-free cavity, within a charge-free cavity in a closed surface, you cannot have a maxima or minima of potential within the volume, right? This is case 1. Moving on to case 2. This, yeah, this is case 1. Case 2. Now let's say in case 2, still the cavity is charge free, but what we are going to do, we are saying that V is 0 on the surface. On the surface, V is 0, potential is 0, and cavity is charge free. In a closed surface, in the volume, there is no charge, there is no charge density, but the potential at the surface is specified and is given as 0, correct? So again, using case 1, we can say that there cannot be a maxima or minima inside the volume, inside the volume, correct? If there can't be a maxima or minima inside the volume, that means V is always going to be 0 within the volume. We can say V is going to be 0 within the volume also. Also, in this case, we have del square V is equal to 0 from the Laplace equation. Since it is a charge-free cavity, del square V is 0, and potential everywhere on the surface is 0. Inside, it cannot be a maxima or minima. So V is 0 everywhere inside the volume. Simple enough. So as far as we can see, it is an extension of case 1 itself. But we have specified it as case 2 because we are going to use it in case 3 and 4. How? Let's see. In case 2, we took a charge-free cavity and we took a specific potential that is 0 on the surface. In case 3, we are going to change one thing. In case 3, we are taking still a charge-free cavity, any cavity, charge-free cavity, closed surface. But the potential at the surface is a function of R. That means it is variable in space. It is variable in space. It can be anything. It is properly defined but fixed with time. It is not varying with the time. It is fixed with the time, but it can be anything with space. I mean, it can be 10 volts at this point, 20 volts at this point. It doesn't matter. But whatever the potential is, it is fixed now. And inside, there is no charge cavity. Now our claim is that there can be only one type of distribution of potential function inside the cavity, or you can say we have to find whether it is possible or not to have two functions or more than two functions of potential inside the volume which will satisfy this boundary condition. This is what? This is a boundary condition. This is a boundary condition. What we have to find out? We have to find out whether or not it is possible to have more than one function, more than one distribution of potential within this volume which will satisfy this boundary condition. Correct? The answer for this question is there can be only one distribution of potential. There can be only one function of potential. The answer or the distribution of potential is going to be unique. It's not going to vary for the particular boundary condition. And now we are going to prove it. How we are going to prove it? Using the approach which we have used in the first method, by contradiction, right? So let's prove it using contradiction. So let's assume that we have two functions. We are going to prove by contradiction. So let's assume that there exist two functions of potentials V1R and V2R inside this volume, and these both will satisfy the boundary condition. Which boundary condition? That the potential at the surface will turn out to be V naught R. That the potential at the surface will turn out to be V naught R. Correct? That means V1R equal to V2R equal to V naught R at the surface. Correct? Now we define a third function, V3R, given by V1R minus V2R. We defined a third function, V3R, which is equal to V1R minus V2R. And the value of V3R at the surface will be 0. Why? Because V1R and V2R are equal. So V3R at the surface is 0. Right? We define V3R as difference of V1 and V2. Since V1 and V2 are same at the surface, then V3R will be 0. Now again, using the Laplace equation, del square V3 is equal to del square V1 minus del square V2. Now del square V1 is 0. Why? Because it is charge free cavity. Del square V2 is also 0 because it is a charge free cavity. So del square V3 R is 0. Del square V3 R is 0. And V3R at surface is also 0. Now potential, there is one function of potential which is 0 at the surface, and del square of that function of potential is 0 inside the surface or inside the volume. Then isn't it the second case that V is 0 and del square V is 0 inside the volume? Correct? That means everywhere inside the volume V will also be 0. Everywhere inside the volume V3 will also be 0 within the volume. Using case 2, we can write V3 will be 0 within the volume. And what is V3? V3 is V1 minus V2R. That means V1R and V2R are nothing but same. So we cannot have two different functions. We will have a unique distribution of potential if we have a charge free cavity and there is a fixed distribution of potential on the surface, on the closed surface. So we will have only a unique solution of potential distribution with space if we have a charge free cavity and there is a fixed potential at the surface. It might be varying with space, but it is fixed with time. Correct? This is our third case. Logically, our fourth case will be a development of the third case, an improvement of the third case, difficulty level will increase. So what we are going to do in the fourth case, in case 4, we have, now we don't have a charge free cavity. The 3 cases with charge free cavity are done. Now in this case, there is a distribution. It is a fixed distribution. Rho r is fixed with time again. It can vary with space, doesn't matter to me. With the time, it is fixed. Correct? And the potential at the surface is given. V is equal to V naught R. It is again similar, V naught R. It can vary with space, but fixed with time. It doesn't change with the time. Our claim again is that there will exist only a unique distribution of potential within the closed surface. What is our claim? Our claim is within this volume, within this closed surface, potential can have only one distribution. पोटेंशियल का एक ही फंक्शन आएगा, उसके 2 3 4 या इनफिनिट सॉल्यूशंस नहीं हो सकते. Now to find that, in order to find that, we are going to do completely we are going to do it similar to the case 3. What we are going to do is we are going to assume that there are, let's say there are two functions v1r and v2r which both satisfy the boundary condition. What are the boundary condition? That v naught is v is v naught r at the surface, v1r equal to v2r equal to v naught r at surface. Again, let's define v3r as a difference of v1r minus v2r. The first thing that we are going to write is v3 is going to be 0 at surface. Correct? v3r is going to be 0 at surface. Now all that is left for us to prove is that del square v3r is going to be 0 inside the volume. If del square v3 is 0 inside the volume, then it will again become similar to the second case, and we can say v1 and v2r are one and the same. Correct? So let's do that. Using again this equation, take del square on both sides, del square v3r, del square v1r minus del square v2r. Del square v1r, rho r by epsilon naught with a negative sign, minus rho r by epsilon naught with a negative sign. Now rho r is whatever the charge density is, it's not going to change, right? It is fixed. With space, it is fixed, right? So what we are getting is del square v3. Again, it is going to get cancelled. So del square v3r is 0 throughout the volume, and v3 is 0 at the surface. The combination of this result and this result is exactly same as that of case 2. So we can say that V3 is always going to be 0 at all points within the volume. And if V3 is 0, that means V1R minus V2R is 0. That means V1R and V2R are one and the same. These are one and the same. So if we have a fixed charge distribution and a fixed potential at the boundary of any closed surface, we can say that there is always going to be a unique solution of potential at any point within that surface. Let me repeat. If we have a unique charge distribution in a closed surface and potential is defined at the surface which is fixed with time, then there will be a unique solution of potential or unique potential function within that closed surface. There cannot be two solutions. And if potential is going to be unique, distribution of potential is going to be unique, then obviously electric field is going to be unique. It is not going to be more than one functions. It is going to be unique. Correct? So this is uniqueness theorem. For any fixed distribution of charge and fixed potential at the boundary surface, the potential distribution within that closed surface will remain fixed with time. There is also one more case in uniqueness theorem, but that is not related to us. So that will not give us any meaningful insight in the method of images. So we are ignoring that. All these four cases constitutes uniqueness theorem. Right? For a change, there is not a lot of mathematics as it was in curl and divergence. We can see it's quite simple, straightforward, but logical at the same time. If there are any doubts, feel free to drop that in the comment section. I'll reply to them. For today, this is it. In the next video, I'll start with method of images for a sphere, for a metallic sphere. See you in the next video. Bye bye.